right, today we're jumping into a really core piece of chemistry, energy. We're going to figure out exactly why some chemical reactions, like a fire, give off incredible heat, while others can literally make things freeze solid. Let's get into it.
I mean, have you ever really stopped to think about it? A campfire and one of those instant cold packs are both just chemical reactions happening. One is combustion, giving off that awesome, cozy heat. The other, well, it involves salts dissolving, and it literally pulls heat out of you. How can two reactions have such wildly different effects?
Well, the answer, not surprisingly, is all about energy. More specifically, it's about whether a reaction is pushing energy out into the world or pulling energy in from the world. And to really get that, we need to define a couple of key terms.
So, first up, we need to understand the arena where all this energy swapping is going on. In chemistry, we call this the system and the surroundings.
Chemists have this really brilliant way of simplifying things. They basically divide the entire universe into just two parts. The system is the chemical reaction we're actually looking at, and everything else, the beaker, the air, you, me, the rest of the planet, is the surroundings. The whole idea here is that energy is constantly flowing between these two.
So just to be super clear, we always look at energy changes from the perspective of the system. Is the system losing energy or is it gaining energy? That one little question is the key to everything that comes next.
And that question immediately splits reactions into two big categories: exothermic, where energy exits the system, and endothermic, where energy enters the system.
And you can see the difference so clearly in these graphs. Take a look at the exothermic one on the left. See how the reactants start with a bunch of energy and the products end up way down at a lower energy level? So where did that extra energy go? It was released. Now look at the endothermic graph. The reactants start low and actually have to absorb energy just to get up to the higher energy products.
So for exothermic reactions, the main thing to remember is they're giving energy away. That campfire is the perfect example. The wood and the oxygen, that's our system, they release a ton of energy as heat and light into the surroundings. That's why you feel warm. The system loses energy and you gain it.
Endothermic reactions, of course, do the exact opposite. The instant cold pack is our system. For that reaction to even happen, it has to suck in heat energy from the surroundings, which is your sore ankle. So the system gains energy, and you lose heat. That's why it feels so cold to the touch.
Okay, but you know chemists, giving heat or taking heat isn't precise enough. They need a way to actually measure this energy change. And that's where a concept called enthalpy comes into play. Now, don't let the fancy name scare you. Enthalpy change, which we write as delta H, is really just the official score. It's a hard number that tells us exactly how much heat the system either gave away or took in. And the sign on that number tells you the whole story. If delta H is negative, it means the system lost energy. It was an exothermic reaction. If delta H is positive, the system gained energy. It was endothermic. So negative means heat exits, positive means heat gets pulled in. It's as simple as that.
Okay, so we know energy is moving around, but why? I mean, what is actually happening at a molecular level to cause all this? Well, it all comes down to the breaking and making of chemical bonds. This is probably the most important idea to really get. The best way to think about it is like a business deal for molecules. First, you have to invest or spend energy to break apart the old chemical bonds in your starting materials. That's your cost. That's energy in. But then, when new, more stable bonds form to make your products, you get a payout. That's your profit. That's energy out. So, that overall enthalpy change, or delta H, is just the net profit or loss from that whole transaction. You figure out the total energy it costs to break all the bonds, then you subtract the total energy you get back from forming all the new ones. The result tells you if you came out ahead or behind.
Let's look at a real-world example, burning methane, which is the main stuff in natural gas. You can see here, it costs 2,640 kilojoules of energy to break all the bonds in the methane and oxygen molecules. But, and this is the good part, when the new bonds form in carbon dioxide and water, you get a massive payout of 3,458 kilojoules back. So what's the bottom line? We got way more energy out than we had to put in. The final delta H is negative 818 kilojoules per mole. And what does that negative sign tell us? It's an exothermic reaction, which makes total sense, right? We're burning fuel. Of course it's releasing a ton of heat. Now, this isn't just about feeling something hot or cold.
Understanding these energy changes lets chemists do something that's almost like a superpower. It lets them make predictions.
Seriously? Knowing the delta H helps us predict if a reaction is likely to be spontaneous? In other words, if it will just happen all by itself, without you having to constantly add energy to keep it going.
I mean, it makes sense if you think about it. Nature tends to favor lower energy states. Things roll downhill, not up. Exothermic reactions release energy and end up in a much lower, more stable state. That's exactly why something like rust just happens on its own. It's an energy-releasing exothermic process. And that brings us to a final, really fascinating question. If nature loves low energy so much, why do some endothermic reactions, reactions that absorb energy and move to a higher energy state, still happen spontaneously? Think about an ice cube melting in a warm room. What's going on there? That's the other part of this amazing story. Thanks for watching.